to study the sun. In fact, SDO will change textbooks and help in some way or another everyone here in this room today, folks watching this program live via NASA television around the world and on our website at www.nasa.gov. And in fact, all of life on Earth, SDO will affect. Ladies and gentlemen, boys and girls, you will see the sun as never seen before today. We have a lot to cover. Our panelists will give brief presentations, and then we will open it up for questions from around the country. Let me introduce you to these incredible scientists. First up, Dean Pesnell, SDO project scientist from NASA's Goddard Space Flight Center in Greenbelt, Maryland. Alan Teitel, principal investigator, atmospheric imaging assembly, Lockheed Martin Solar and Astrophysics Laboratory in Palo Alto, California. Next will be Philip Scherer, principal investigator, helioseismic and magnetic imager, Stanford University in Palo Alto. Next up would be Tom Woods, principal investigator, extreme ultraviolet variability experiment from the Laboratory for Atmospheric and Space Physics from the University of Colorado in Boulder. And Madhulika Gahutakurta, we like to call her Lika, the SDO program scientist at NASA headquarters in Washington. But before we get to them, we're going to set the stage. The director of NASA's office that studies the sun and its interaction with Earth and the solar system, the area of science called heliophysics, will set the stage. The director, Richard Fisher.
We are all living in the outer atmosphere of a star, and that's our sun. And its variability influences the Earth and the planets and the space in the solar system itself. Now today, our goal is to show you the first images, the first data from the Solar Dynamics Observatory, which people will refer to as SDO. This was launched relatively recently in last February, and it's taken several weeks to commission the observatory. And this is like getting the power systems right, getting the temperatures right, getting the pointing fixed so that it's working correctly. It's taken several weeks to do, and it has worked very well. The spacecraft is one of the most flawlessly operating ones I've ever seen. The first images are now in hand, and these are truly spectacular, and they show the details of our sun that have not been available to us before in a comprehensive and a multidimensional manner. The impact of this observatory on the physics of stars, solar physics, solar terrestrial research, and in the field of space weather will be truly revolutionary. And I mean that revolutionary in the sense that the way the Hubble Space Telescope was in fact a tool for revolutionizing astrophysics over the last 2 decades. Without going into it any further, let me introduce Dean Pesnell, who will take the lead.
All right. Thanks, Dick. I'm Dean Pesnell, and I'm sure happy to be here today. SDO is doing great, and our instruments are doing better. But let's start with a launch sequence. SDO was launched into a partly cloudy sky on February 11th, 2010. It took us about 12 more burns to get into our correct orbit, and then we began turning on all the systems, getting the instruments running. And the biggest thing is first we need power, so we get our solar arrays. Second, we need to be able to talk to the spacecraft, so we get our radio antennas. And then we need the instruments to open their doors so that they can start sending back data. We are now sending our high-speed data of about 4 16-megapixel images per every 3 seconds to the ground. SDO is the first mission in the Living with a Star program. It's designed to study the sun and how the sun affects us here on the Earth. Most of these effects come from the magnetic field of the sun, and we're going to see today that that magnetic field is never the same twice. It's always changing. Today we will show some of the earliest data from SDO. We will see new things with each instrument. The first is the helioseismic and magnetic imager. HMI will measure the waves rippling across the surface of the sun and the strength and direction of the magnetic field at the surface of the sun. Using those waves, we can actually look inside the sun, and in fact, we can look all the way through the sun and see what's happening on the other side. It's a great thing that we've been using for a while, and HMI will allow us to do better. The next instrument is the Extreme Ultraviolet Variability Experiment, or EVE. That's built by the University of Colorado, and that measures the heartbeat of space weather, the extreme ultraviolet emissions of the sun. This data will tell us what the sun is doing to the upper parts of our atmosphere as it affects our radio communications and causes satellite drag to bring satellites down. Our first picture from EVE doesn't look anything like it should. It's a beautiful image of a CCD image of the spectrum where things that are red are bright and things that are blue aren't bright. But the cool thing about EVE is they found a little spot on the CCD, and in the lower right-hand corner, you can see a small image of the sun, and that's in very short wavelength X-rays. Our third instrument is the Atmospheric Imaging Assembly. That was built at the Lockheed Martin Solar Astrophysical Laboratory and will bring us extraordinary image of the sun's corona and chromosphere. AIA will record images of the full disk EUV sun at a pace and with more channels than we have ever before achieved. This will allow us to zoom in on small regions and see far more detail in both time and space. Here we see an image from AIA at about 80,000 Kelvin. We have two more, and there is successively hotter parts of the sun, up to about 2 million Kelvin. We have so many channels on AIA that we're actually having problems deciding on what false colors to use to represent these images. So I hope you understand our problem. The first movie I saw from AIA was taken the very day that they made the detectors cold and could take a good picture. And we're going to show that next. It's a little part of the sun, and we see what's called a prominence eruption coming off of the surface. Now, it's not a very long movie. We're going to loop it around a couple of times so you can see it. But I called in another solar physicist to look at this movie, and he laughed and said, well, that disproves another theorist's theory. So, of course, I went to the other theorist, and I said, well, what do you think about that? And he said, well, it may disprove that theory, but I have another theory that also explains this. So we're already learning new things from the images that we're seeing and from our instruments. But this is only the first view. And now I'm going to let Alan Teitel from the AIA instrument talk about even more of the images that they've been able to take since they started. Alan?
Thanks, Dean. Thank you for showing my movie. I wonder if we could have the first slide, please. Okay. This is not a cartoon. This is the real instrument. You can see the 4 AIA telescopes, and behind it, the SDO spacecraft. This is an effort of a number of years